November 24, 1943, North Pacific waters off Alaska. The SS John P. Gaines, 6 months old, built using revolutionary American welding techniques that promised to win the war through sheer production speed. Through 40-foot swells and winter darkness, something was happening that naval architects said was impossible. The hull, 441 feet of solid American steel, was splitting apart like kindling, not at the welds, not at the joints, through the metal itself. 10 crew members would die as the bow section sank beneath the waves. For 50 years, riveted ships had flexed through Atlantic storms, their hulls bending and moving like living things. The Titanic, the Lusitania, every great vessel built with 3 million individual rivets, each one allowing the ship to breathe with the ocean. But Henry Kaiser's Liberty ships were different. Welded, solid, monolithic, rigid as bridges. American innovation had replaced European tradition, building ships in 45 days instead of 6 months, using workers who learned welding in 2 weeks instead of craftsmen trained for years. The production miracle that was supposed to save Allied shipping from German U-boats was now destroying itself from within. And the most terrifying part? Nobody understood why perfectly good ships were snapping in half in calm seas. December 1940. The cables arrived at shipyards from Philadelphia to Portland, carrying the same impossible mathematics. Britain needed 60 new cargo vessels immediately. 600,000 tons of shipping to replace what German U-boats had sent to the bottom of the Atlantic in the past 3 months alone. Traditional shipbuilding required 6 months per vessel using riveted construction methods refined over 50 years of maritime engineering. Adolf Hitler's timeline for starving Britain into submission: 12 months. William Francis Gibbs stood in his Philadelphia office, surrounded by blueprints of elegant passenger liners that had dominated Atlantic crossings for 2 decades. At 57, he embodied everything the American maritime establishment represented: methodical precision, proven techniques, and hard-won respect for the ocean's power to destroy careless engineering. The British request spread across his mahogany desk represented mathematical impossibility. Each riveted cargo ship required 30,000 workers and 26 months of careful construction. 3 million individual rivets installed by 2-man teams using techniques unchanged since the Titanic slid down Belfast slipways in 1911. Mathematically impossible, Gibbs declared to the Maritime Commission representatives who had traveled from Washington seeking miracles. The numbers were unforgiving. Britain's merchant marine was disappearing beneath the waves faster than American shipyards could replace individual vessels. German submarines were sinking Allied cargo ships at a rate of 700,000 tons per month. Traditional construction methods, no matter how refined, could not match the pace of destruction. Yet abandoning proven techniques meant risking crew lives on untested innovations. The Titanic's construction had required every rivet to be heated cherry red in portable forges, then driven home by pneumatic hammers while still glowing. 2-man teams, one holding the rivet steady, another driving it flush, repeated this process 3 million times per ship. The overlapping steel plates created natural flexibility, allowing hulls to bend and twist with ocean swells without fracturing. Gibbs had studied every major maritime disaster of the past 50 years. Ships failed when they fought the ocean's movement rather than flowing with it. Riveted construction was not merely tradition, it was survival. But in California, Henry Kaiser was examining the same British requirements through entirely different eyes. At 58, the dam builder had never set foot on a ship's deck, never studied naval architecture, never learned the maritime traditions that governed East Coast shipbuilding. His qualification was singular and revolutionary. He had completed the Hoover Dam 2 years ahead of schedule using prefabrication techniques and a construction method that traditional engineers had declared impossible: electric arc welding instead of individual riveting. Kaiser's audacious proposal arrived at the Maritime Commission on December 15th. Weld ships like building bridges. Replace 3 million individual rivets with continuous steel joints fused at temperatures exceeding 3,000 degrees Fahrenheit. Build hull sections at multiple inland locations, then transport them to coastal shipyards for final assembly, like constructing a massive steel puzzle. Time per ship, 45 days. Cost reduction, 40%. Production capacity, unlimited, constrained only by steel availability and workforce size. The welding process itself represented a fundamental departure from maritime tradition. Instead of overlapping plates held together by individual rivets, welded construction created monolithic hulls, single continuous structures without joints or seams. Electric arc welding, perfected in American steel mills and bridge construction, used high-voltage electricity to melt steel at the molecular level, creating bonds stronger than the original metal. Kaiser's engineers calculated that welded joints could withstand pressures that would shear traditional rivets, while eliminating the countless potential failure points that riddled riveted construction. The Maritime Commission faced an impossible choice between proven inadequacy and revolutionary uncertainty. Traditional methods guaranteed ships that would survive ocean conditions, but could never match German destruction rates. Kaiser's welding techniques promised production speeds that could overwhelm submarine warfare, but had never been tested in maritime applications. No welded cargo ship had ever crossed the Atlantic. No maritime engineer understood how monolithic hulls would respond to storm conditions that had tested riveted vessels for decades. Desperation made the decision inevitable. By January 1941, Kaiser received contracts for 60 Liberty ships, standardized cargo vessels designed for maximum production efficiency rather than elegance or speed. 441 feet long, 56 feet wide, capable of carrying 9,000 tons of military supplies across both Atlantic and Pacific theaters. The design deliberately sacrificed everything except cargo capacity and construction speed. No luxury accommodations, no advanced navigation equipment, no architectural beauty, simply floating warehouses designed to be built faster than German torpedoes could sink them. But as construction began at Kaiser's hastily built shipyards along the West Coast, the full scope of the challenge emerged. Welding required 50 miles of continuous joints per ship, executed to tolerances measured in thousandths of an inch. The workforce, mostly women and minorities replacing men drafted into military service, needed to master techniques that existed in no maritime textbook. Shipyard welders learned their craft in 2 weeks instead of the 6 months traditionally required for riveting apprenticeships. Quality control meant inspecting invisible molecular bonds rather than counting visible rivets. Most ominously, nobody understood how welded ships would behave in actual ocean conditions. Traditional riveted hulls allowed controlled flexibility. Steel plates could shift slightly against each other, absorbing wave energy through thousands of individual joints. Welded hulls were rigid, monolithic structures that would either flex as single units or fracture catastrophically. What happened when a completely rigid structure met a 40-foot Atlantic wave moving at 30 knots? The mathematics were theoretical. The stakes were measured in human lives crossing submarine-infested waters in untested vessels. By late 1942, Kaiser's 7 shipyards employed 200,000 workers producing Liberty ships at unprecedented rates. The SS Robert E. Peary was assembled in 4 days, 15 hours, 29 minutes, a world record that captured international headlines and made Kaiser a folk hero. Miracle Man magazine covers celebrated the industrialist who promised to outbuild Hitler through American production efficiency. But winter was approaching in the North Atlantic, and the first reports were beginning to trickle back from ship captains who had noticed something troubling: hairline cracks appearing in solid steel plates where no cracks should be possible. By spring 1942, Kaiser's production system had achieved what maritime experts had declared impossible. The Richmond Shipyard No. 2 in California operated with the precision of Henry Ford's assembly line, adapted for vessels weighing 10,000 tons. Specialized crews moved between construction bays like orchestra sections, each team responsible for a single aspect of ship assembly. Hull welders worked exclusively on bottom plates. Deck crews installed only superstructure. Engine teams focused solely on propulsion systems. The result was unprecedented efficiency that reduced construction time from months to weeks. The technical breakthrough exceeded every prediction. Welded hulls proved 30% lighter than riveted equivalents, eliminating thousands of pounds of overlapping steel plates and rivet heads that added weight without structural benefit. Watertight integrity surpassed traditional construction because continuous welded seams created perfect barriers against flooding, unlike riveted joints that inevitably leaked through microscopic gaps between plates. Hull surfaces remained smooth and hydrodynamically efficient, increasing cargo capacity and reducing fuel consumption during Atlantic crossings that could determine the difference between successful supply runs and submarine victories. Edgar Kaiser Sr. managed day-to-day operations with mechanical precision that translated his father's vision into measurable production metrics. At 40, he had internalized the systematic approach that built the Hoover Dam ahead of schedule, viewing shipbuilding as another construction project to be optimized through workflow analysis and resource allocation. Each Liberty ship required 2,800 tons of steel, organized into prefabricated sections that could be manufactured simultaneously at multiple locations. Bottom plates were cut and shaped at inland facilities, then transported by rail to coastal shipyards for final assembly. Superstructure components arrived from subcontractors across the West Coast, timed to arrive precisely when welding crews were ready to install them. The workforce transformation represented a social revolution disguised as wartime necessity. Women comprised 30% of Kaiser's welding crews, learning precision techniques in 2 weeks that traditionally required 6 months of apprenticeship. Rosie Chen exemplified the new generation of shipyard workers, 24 years old, Chinese-American, trained on electric arc welding equipment that could join steel plates with molecular-level bonds stronger than the original metal. Her daily routine began at 6 in the morning with safety briefings that emphasized the critical nature of each weld. A single defective joint could compromise watertight integrity for an entire cargo hold carrying tanks and aircraft destined for European battlefields. Production statistics reached levels that defied traditional maritime construction assumptions. By mid-1943, 18 Kaiser shipyards employed 200,000 workers operating in 3 shifts around the clock. Daily output: 3 complete Liberty ships launched and commissioned for immediate service. Each vessel measured 441 feet in length and 56 feet in beam, capable of transporting 2,840 jeeps or 440 Sherman tanks or 230 million rifle rounds across submarine-infested Atlantic shipping lanes. Total production exceeded every maritime commission projection, with Liberty ships comprising 27% of all wartime American vessel construction. The economic transformation proved equally revolutionary. Construction costs dropped from $3.2 million per ship using traditional riveted methods to $1.8 million through welded assembly line techniques. Steel consumption decreased by 40% per vessel, while cargo capacity increased by 15%. Labor requirements fell from 30,000 workers per ship over 6 months to specialized crews of 5,000 workers completing vessels in 45 days. The mathematics of industrial warfare favored American production capacity over German submarine destruction rates for the first time since the Atlantic battle began. Kaiser's innovation extended beyond construction techniques to fundamental shipbuilding philosophy. Traditional maritime engineering emphasized individual craftsmanship, with master shipwrights overseeing every aspect of vessel construction from keel laying to final sea trials. Kaiser's approach treated ships as standardized industrial products, manufactured using identical specifications and interchangeable components. Engine rooms contained identical propulsion systems. Bridge equipment followed standard layouts. Even minor fittings were standardized across all Liberty ship production, enabling rapid repairs and crew training that could save critical hours during wartime operations. The strategic implications became apparent as convoy statistics improved dramatically. German U-boats had been sinking Allied merchant vessels faster than traditional shipyards could replace them, creating a mathematical equation that favored Axis victory through maritime strangulation. Kaiser's production rates reversed this calculation, delivering new cargo capacity faster than submarine warfare could eliminate it. British ports that had faced supply shortages throughout 1941 were receiving American jeeps, tanks, aircraft, and ammunition in quantities that exceeded consumption for the first time since Germany launched its Atlantic campaign. International recognition followed production success. British maritime officials who had initially dismissed American welding techniques as untested innovation publicly acknowledged the superiority of Kaiser's methods. Soviet naval engineers requested technical specifications for welded construction, recognizing that their own shipbuilding capacity could be revolutionized through American techniques. Even neutral nations began adapting electric arc welding for merchant vessel construction, acknowledging that traditional riveting had become obsolete almost overnight. But veteran ship captains were beginning to notice patterns that production statistics could not capture. Liberty ships performed flawlessly in warm Pacific waters, maintaining structural integrity through typhoons that would have tested any vessel. However, reports from Atlantic convoys suggested different behavior in cold northern waters. Captains mentioned minor hull flexing that seemed unusual for welded construction. Engineering inspectors found hairline stress marks in locations that should have been immune to fatigue. Most puzzling, these signs appeared exclusively during winter crossings, never in temperate conditions where identical ships showed no structural concerns. The anomalies seemed insignificant compared to production victories that were reshaping global maritime warfare. Kaiser had proven that American industrial methods could revolutionize any field, transforming shipbuilding from craft tradition to mass production in less than 2 years. Liberty ships were crossing both Atlantic and Pacific theaters, delivering the military supplies that would determine Allied victory or defeat. The welding techniques that maritime experts had declared impossible were now recognized as the future of ship construction, destined to make riveted vessels as obsolete as sailing ships in an age of steam power. Winter 1942 brought the first systematic reports of structural problems that challenged Kaiser's production triumph. Maritime Commission investigators documented 150 significant hull cracks across the Liberty ship fleet, concentrated almost exclusively in vessels operating North Atlantic convoy routes. The SS Schenectady split completely in half while moored peacefully in Portland's harbor on January 16, 1943. The fracture occurred not during storm conditions but in calm water with temperatures hovering near freezing, no external stress, no heavy seas, simply catastrophic failure of what should have been the strongest portion of the hull. Edgar Kaiser Sr. responded with characteristic systematic precision, implementing enhanced quality control procedures that treated the crack epidemic as a production problem requiring operational solutions. Welding certification programs expanded from 2 weeks to 4 weeks of intensive training. X-ray inspection equipment arrived at all shipyards, enabling engineers to examine molecular-level weld integrity invisible to surface examination. Certified welding operators received wage increases and additional supervision to ensure consistent technique across all construction bays. The solution appeared obvious. Better training would eliminate shoddy workmanship that caused structural failures. Rosie Chen exemplified the improved standards, completing advanced welding certification that emphasized penetration depth and cooling rates for joints exposed to extreme stress. Her daily routine now included detailed inspection of each completed weld using magnetic particle testing that revealed microscopic flaws potentially invisible for months until catastrophic failure. The enhanced procedures added 3 days to construction schedules, but seemed to address the fundamental cause of hull cracking. Quality control replaced speed as the primary shipyard metric, with production bonuses tied to structural integrity rather than completion dates. The Maritime Commission's investigation focused on human factors that could explain the crack epidemic. Wartime production pressures had forced shipyards to hire inexperienced workers, many of whom learned welding techniques in weeks rather than the years traditionally required for maritime construction. Women and minority workers, despite their dedication and rapid skill acquisition, lacked the institutional knowledge that prevented subtle errors in joint preparation and cooling procedures. The conclusion seemed straightforward. Improved training and stricter supervision would eliminate the structural problems that threatened Kaiser's revolutionary production system. Spring 1943 brought encouraging evidence that the enhanced procedures were working. Crack reports declined significantly as certified welders implemented new standards for penetration depth and joint cooling. Ships launched after March first showed dramatically improved structural performance, with hairline fractures virtually eliminated from inspection reports. Kaiser's reputation began recovering as maritime officials acknowledged that American innovation, properly implemented, could indeed revolutionize shipbuilding without compromising safety standards that protected crew lives. But veteran mariners noticed patterns that escaped engineering analysis. Captain Harold Morrison, who had commanded both riveted cargo ships and New Liberty vessels, observed that structural problems occurred almost exclusively during winter months. Ships that showed perfect integrity during summer Atlantic crossings developed stress fractures when water temperatures dropped below 40 degrees Fahrenheit. Most puzzling, identical vessels operating Pacific routes, where water remained relatively warm year-round, showed no comparable structural issues despite encountering typhoons that exceeded Atlantic storm intensity. The geographic pattern defied conventional engineering wisdom. If welding quality was the primary factor, structural failures should occur randomly across all operating theaters. Instead, cracks concentrated in specific ocean regions characterized by sustained cold water temperatures. Liberty ships crossing tropical Atlantic routes showed excellent structural performance, while vessels following northern convoy routes to Murmansk and Iceland reported repeated stress fractures requiring emergency port calls for structural repairs. The correlation with temperature seemed too consistent to represent coincidence. Morrison's observations reached Maritime Commission headquarters through routine convoy reports that documented unusual hull behavior in cold water conditions. Liberty ships operating in northern waters exhibited different flexing characteristics than identical vessels in temperate zones. Hulls that remained rigid and strong in warm conditions seemed to become more brittle when water temperatures approached freezing. The phenomenon contradicted everything naval architects understood about steel behavior, which should remain consistent regardless of environmental temperature variations. Dr. Constance Tipper received her first steel samples from failed Liberty ships in late 1943, though the significance of her work remained unrecognized by American maritime officials focused on production solutions rather than metallurgical research. At Cambridge University, she had spent 3 decades studying how metals behave under stress, developing impact testing procedures that revealed material properties invisible to conventional engineering analysis. Her laboratory equipment could measure how steel fractures at the molecular level, identifying failure mechanisms that occurred too rapidly for human observation. The steel samples from Liberty ship cracks revealed anomalies that challenged fundamental assumptions about material behavior. Fracture surfaces showed characteristics of brittle failure rather than ductile tearing, suggesting that the steel itself had changed properties under specific conditions. Most significantly, crack propagation patterns indicated failure speeds approaching the velocity of sound through solid steel, mathematical impossibility according to accepted engineering principles. Something was causing perfectly good steel to behave like glass under conditions that should not affect structural integrity. Meanwhile, Kaiser's shipyards continued record production, launching 3 Liberty ships daily while implementing enhanced quality procedures that seemed to address the structural problems. The crack epidemic appeared to be a temporary setback caused by wartime production pressures rather than fundamental flaws in welding technology. Maritime Commission officials praised the systematic approach that identified and corrected quality control issues within months of their discovery. American innovation had proven its ability to adapt and improve, maintaining production efficiency while ensuring crew safety. But the approaching winter of 1943 would test Liberty ship construction under conditions that no amount of quality control could address. As convoy routes shifted northward to avoid German submarine concentrations, more vessels would encounter the sustained cold water temperatures where steel behavior changed in ways that conventional engineering could not predict or prevent. The molecular forces that governed material strength operated according to physical laws that remained invisible to production managers. Focused on welding technique and worker training, the stage was set for catastrophic failures that would reveal the true nature of the structural problems plaguing Kaiser's revolutionary shipbuilding program. Not human error, not inadequate training, but fundamental misunderstanding of how steel itself responds to environmental conditions that American engineers had never encountered in their previous construction experience. The ocean was about to teach American industry a lesson in materials science that would revolutionize engineering practice for decades to come. November 24th, 1943. The SS John P. Gaines sailed through 35-foot swells in the North Pacific, 6 months old and carrying 8,000 tons of military supplies bound for Alaska. Built at Kaiser's Richmond shipyard using the most advanced welding techniques available, the vessel had passed every structural inspection and represented the pinnacle of American shipbuilding innovation. Water temperature hovered at 38 degrees Fahrenheit. Wind conditions were moderate. Nothing in the weather pattern suggested unusual stress on the hull structure. At 1400 hours, Chief Engineer William McDonald noticed unusual vibrations in the engine room that seemed unrelated to propulsion machinery. The ship's hull was flexing differently than expected, exhibiting rigid behavior that contradicted the normal give-and-take motion of steel construction in ocean swells. McDonald had served on both riveted cargo ships and Liberty vessels throughout the war, developing an intuitive understanding of how properly constructed hulls should respond to wave action. The John P. Gaines was moving like a single, inflexible beam rather than a maritime structure designed to work with ocean forces. The catastrophic failure began at the No. 3 cargo hold, where a stress concentration at a square hatch corner initiated a crack that propagated through solid steel plate at nearly the speed of sound. The fracture did not follow weld lines or joint boundaries. It cut directly through base metal that should have been the strongest part of the hull structure. Within seconds, the crack extended from deck to keel, compromising the structural integrity of the entire midship section. The vessel's back broke with a sound that survivors described as similar to a massive tree trunk snapping under impossible stress. 10 crew members died as the bow section tilted and sank beneath the frigid Pacific waters. The stern portion remained afloat long enough for 28 survivors to launch lifeboats and radio distress signals that brought rescue vessels within 6 hours. Coast Guard investigators who examined the floating stern section found fracture surfaces that defied conventional understanding of steel failure. The metal had broken with characteristics of brittle fracture rather than ductile tearing, as if the steel itself had become fundamentally different. Material under cold water conditions. The John P. Gaines disaster triggered emergency investigations across the entire Liberty ship program. Within weeks, additional catastrophic failures confirmed that the problem extended far beyond isolated incidents. The SS Esso Manhattan split completely in half while crossing the Atlantic in December, with the forward section sinking before crew members could launch lifeboats. The SS Ponegonset developed a crack extending from deck to keel while loading cargo in Boston Harbor, forcing evacuation of dock workers when the hull began separating along the fracture line. Maritime Commission investigators convened emergency hearings in Washington, summoning shipyard executives, naval architects, and welding experts to explain how vessels that had passed rigorous quality inspections could fail so catastrophically. Edgar Kaiser Sr. presented detailed production records demonstrating that the failed ships had been constructed using enhanced procedures implemented after the earlier crack reports. Welding operators were fully certified. Materials met all specifications. Quality control exceeded peacetime standards. Yet perfectly constructed ships were breaking in half under conditions that should not have challenged structural integrity. William Francis Gibbs testified with grim satisfaction that vindicated his earlier warnings about untested welding techniques. Traditional riveted construction had never experienced comparable catastrophic failures because overlapping steel plates provided natural crack arresters that prevented fractures from propagating across entire hull sections. Riveted joints allowed controlled flexibility that absorbed wave energy through thousands of individual connection points, while welded construction created monolithic structures vulnerable to complete failure if cracks initiated anywhere in the hull. The cascade of failures accelerated throughout winter months as more Liberty ships encountered the cold water conditions that triggered brittle fracture. By April 1946, 1,031 Liberty ships had been damaged by structural cracking, with 233 declared total losses beyond economical repair. The program designed to save Allied shipping through unprecedented production efficiency was destroying itself at rates that approached German submarine success during the worst periods of Atlantic warfare. Kaiser's reputation collapsed as congressional investigators questioned whether American industrial methods could be trusted with projects requiring absolute reliability. The man who had promised to outbuild Hitler through mass production innovation was now associated with engineering failures that killed American crews more efficiently than enemy action. Newspaper headlines that had celebrated the Miracle Man now portrayed him as a dangerous amateur whose inexperience with maritime engineering had compromised national security during the most critical period of the war. The technical mystery deepened as metallurgical analysis revealed that failed steel components showed no evidence of substandard materials or construction defects. Welding quality met or exceeded specifications. Steel composition matched approved formulations. Joint integrity appeared perfect until the moment of catastrophic failure. The steel itself seemed to be changing fundamental properties under specific environmental conditions that remained invisible to conventional engineering analysis. American materials science lacked the theoretical framework to explain why identical steel behaved completely differently in cold versus warm conditions. Emergency design modifications attempted to address the crisis through engineering solutions that misunderstood the fundamental nature of the problem. Additional welded reinforcements were installed around critical stress points, creating even more rigid structures that actually increased vulnerability to brittle fracture. Inspection procedures expanded to include X-ray analysis of every critical joint, missing the fact that failures initiated in solid base metal rather than welded connections. Quality control became increasingly elaborate while remaining focused on construction techniques rather than material behavior. The Liberty Ship crisis represented more than engineering failure. It challenged American confidence in industrial innovation that had become central to national identity during wartime mobilization. The country that had revolutionized automobile production, built the Hoover Dam, and created unprecedented manufacturing capacity was suddenly confronted with fundamental gaps in scientific understanding that made welding technology appear dangerous rather than revolutionary. Traditional European engineering methods seemed vindicated by American failures that killed crews relying on untested innovations. But across the Atlantic, Dr. Constance Tipper was developing theoretical insights that would transform the disaster into the foundation for modern materials science. Her impact testing revealed that steel behavior changed dramatically at low temperatures, transitioning from ductile to brittle characteristics in ways that had never been systematically studied. The Liberty ship failures were not engineering mistakes. They were accidental discoveries of physical laws that governed material behavior under conditions American engineers had never encountered. The catastrophe would eventually prove that Kaiser's welding technology was not wrong, merely incomplete without proper understanding of the metallurgy that determined when innovation succeeded and when it killed. Dr. Constance Tipper's Cambridge laboratory had accumulated steel samples from 17 failed Liberty ships by February 1944, fragments that arrived with little fanfare from Maritime Commission investigators who viewed metallurgical research as peripheral to their engineering crisis. At 49, she had spent 3 decades studying how metals fracture under stress, work that her male colleagues in Cambridge's engineering faculty considered too theoretical for practical application. Her impact testing equipment, designed to measure how materials behave when struck with precisely calibrated forces, could reveal properties of steel that remained invisible to conventional analysis methods used in shipyard quality control. The first breakthrough came through systematic comparison of fracture surfaces from Liberty ship failures versus samples from riveted vessels that had operated successfully for decades. Under electron microscopy magnification that revealed atomic-level structure, the Liberty ship steel showed characteristics of brittle fracture, clean, crystalline break patterns that indicated the material had shattered like glass, rather than tearing gradually through ductile deformation. Riveted ship steel exhibited completely different fracture characteristics, with rough, fibrous surfaces that demonstrated normal ductile behavior expected from properly functioning structural materials. Tipper's impact tests revealed the shocking truth about steel behavior that American engineers had never encountered. At room temperature, steel samples from Liberty ships exhibited excellent ductility, bending and deforming gradually under increasing stress loads. But when identical steel specimens were cooled to 40 degrees Fahrenheit, the temperature of North Atlantic and North Pacific waters during winter months, the same material became brittle as glass, fracturing suddenly and completely under loads that would normally cause gradual yielding. The ductile to brittle transition temperature represented a fundamental property of steel composition that determined whether structures would bend or shatter under identical stress conditions. The mathematical precision of the temperature effect astounded even Tipper, whose theoretical work had predicted similar phenomena without access to failed structural samples for verification. Steel containing high sulfur content, a characteristic of wartime materials produced under emergency conditions, exhibited transition temperatures as high as 50 degrees Fahrenheit. Below this critical threshold, the atomic structure of steel changed its fundamental response to stress, transforming from a material that could absorb energy through plastic deformation into one that transmitted stress waves at the speed of sound through crystalline fracture patterns. Most significantly, Tipper's analysis revealed why welded construction amplified the brittleness problem, while riveted structures remained immune to catastrophic failure. Riveted ships consisted of thousands of individual steel plates connected by mechanical fasteners, creating natural crack arresters that prevented fractures from propagating beyond single structural elements. Even if one plate became brittle and cracked, the riveted joints would absorb the fracture energy and prevent failure from spreading to adjacent sections. The overlapping construction that traditional engineers had developed through empirical experience inadvertently created the perfect defense against brittle fracture propagation. Welded Liberty ships represented the opposite structural philosophy, monolithic construction that eliminated all barriers to crack propagation. Once brittle fracture initiated at any stress concentration point, such as a square hatch corner or abrupt change in plate thickness, the crack could travel the entire length of the hull at nearly the speed of sound. The continuous welded joints that provided superior watertight integrity and structural efficiency in normal conditions became highways for catastrophic failure when steel entered its brittle temperature range. Tipper's theoretical framework explained every puzzling aspect of the Liberty ship crisis that had baffled American investigators. Cracks occurred almost exclusively in winter because cold water temperatures triggered the ductile to brittle transition in wartime steel. Failures concentrated in northern shipping routes where sustained cold conditions kept hulls below the critical temperature threshold for extended periods. Ships failed in calm seas rather than storms because brittleness made hulls vulnerable to normal operational stresses that would never challenge properly ductile steel. Most importantly, cracks propagated through solid steel plate rather than following weld lines because the base metal itself had become the weakest structural component. The solution emerged not from abandoning welding technology, but from understanding how to apply it properly with knowledge of material behavior that American engineers had never been required to consider. Strategic placement of riveted seams as deliberate crack arresters could preserve the production advantages of welded construction while preventing catastrophic failure propagation. Improved steel chemistry with reduced sulfur content would lower the ductile to brittle transition temperature below typical ocean conditions. Rounded hatch corners and gradual thickness transitions would eliminate the stress concentrations where brittle cracks typically initiated. Tipper's recommendations reached American shipbuilders through technical reports that initially received skeptical reception from engineers focused on production rather than theoretical materials science. The concept that steel itself could change fundamental properties based on temperature seemed to contradict practical experience with construction materials that behaved consistently across normal environmental conditions. But experimental verification of the brittle transition phenomenon using American steel samples gradually convinced Maritime Commission investigators that British metallurgical theory provided the key to solving their engineering crisis. Implementation of Tipper's improvements began with Liberty ships launched after mid-1945, incorporating design modifications that acknowledged the reality of brittle fracture while preserving the production advantages that had revolutionized shipbuilding. Strategic riveted sections interrupted welded construction at critical locations where crack arrest was essential. Improved steel specifications reduced sulfur content below levels that caused high transition temperatures. Structural details eliminated sharp corners and abrupt changes that created stress concentrations in brittle conditions. The vindication was complete and dramatic. Modified Liberty ships with tippers improvements showed zero catastrophic failures even during extended operations in Arctic waters, where original vessels had been most vulnerable. Ships constructed with proper understanding of brittle fracture mechanics proved not just viable, but superior to traditional riveted construction in every measurable performance category. Kaiser's revolutionary welding technology, properly applied with scientific understanding of material behavior, became the global standard for maritime construction that would define shipbuilding for the remainder of the 20th century. But the legacy of the Liberty ship crisis extended far beyond maritime engineering. The accidental discovery of brittle fracture mechanics through catastrophic failures created an entirely new field of materials science that would prevent structural failures across every industry that depended on steel construction. The principles that Tipper developed to explain why ships broke in half would eventually ensure that airplane wings did not crack, bridges did not collapse, and nuclear reactor vessels contained their tremendous internal pressures. American innovation, informed by British scientific rigor, had transformed disaster into the foundation for engineering safety that would protect millions of lives through properly understood materials science.